Hopefully by now, you have learned more about mathematical optimization and now ready to put all that you learned into practice and model a new problem. The case study we see today is inspired by a client project I worked on in the past. Of course, we are using a more simplified version of that problem and with a smaller data set so that you can all follow along and run everything, even if you have Gurobi's restricted license. So let's begin. Think about any of these businesses: a local mom and pop restaurants with their own delivery services, or a home service providers with skilled workers such as landscapers, plumbers, and electricians, or a home healthcare providers that send licensed professionals like nurses to patients' homes. All of these businesses that are often called field service operations require dispatching operators, skilled workers, or technicians to customer locations to perform various services or jobs. The primary objective is to deliver efficient and timely services to customers while juggling a series of constraints and working with limited resources. In field service operations, there are usually a few constraints to consider. One, technician availability. We have limited technicians, and they can have different availabilities and schedules. Two, skill set matching. Not everyone is qualified to do all the jobs, so we need to match the right skill to the right job. Three, customer time windows. The customers have specific time frames during which they are available to receive services. And four, service priority. Sometimes priorities come from the nature of the job. For example, one is urgent and one is not. And sometimes it comes from the customer relationship that we have. For example, we have business customers versus normal customers, or we have an existing customer versus a new one. And the aim in all of these is to efficiently match the technicians to customer service requests with whatever goal that's important to the business, whether to increase customer satisfaction, reduce total time, reduce delay, and so on. So how the operation works. Technicians start their day from a service center, and depending on the business, by the way, this can be called by other names like depot, hub, and so on. When the technicians are dispatched to serve the customers, they carry the equipment necessary for their jobs in one of the company's vans. They leave from the service center they are located at, and after finishing the job of each customer they're assigned to, they return to the center. We call this problem the technician routing and scheduling, or TRS for short. And as the name suggests, it requires assignment, scheduling, and routing of technicians to serve customers, taking into account the priorities, service time windows, processing times, skill requirements, and more. Well, now let's take a quick look at the input data for TRS. In the files provided in the repo, you will find an Excel file called data sc0. In this file, we have three tables: customers, technicians, and location. First of all, the planning horizon is from 7 a.m. to 5 p.m. or 10 hours. When we convert all the time components into minutes, we map 7 to 0, therefore 5 to 600. And in that case, the time horizon you will see is going to be 600 minutes. Of course, this is a common practice to choose a reference point in time and convert all the date-time objects into integers because they will be used as coefficients or even decision variables, and we want to deal with numbers. Okay, let's go back to the input tables. We have customer tables, which contain the information for a customer, their job requests, and their availability. So for example, if we look at customer 1, we will see that they give us a window from 7 to 7:30, but when we are converting them, it becomes 0 to 30, right? The technician tables has information about the technician, about their capacity or availability for the day, which centers they are located at, and also the type of jobs they are qualified to do. So if you see a 1 in a cell associated to each job, it shows the technicians can do that job. So for example, here you're seeing that this technician can do this job and this job and this job and this job and this job, but not this one, right? We also see how long it takes to finish each job, right? So we will see them up here. And of course, we are seeing the priority of the job as well. So higher the number, higher the priority. So for example, a critical repair with a value of 4 has a higher priority than a regular repair with a value of 1. And lastly, we have the locations table, which just shows us the travel time in minutes between different locations. Here are the assumptions that we need to have for TRS problem. If we use a technician, they leave from their center, do their jobs, and then return to the center. We saw that technicians have their own availability in terms of how many hours they work per day. So we must respect that. And of course, we must respect the 10-hour planning horizons that we have. We may not be able to serve all the customers, but if a customer's job is selected, then only one technician with the right skill is assigned to it. The customer's time window must be respected. So a technician should arrive at the job during the window of the customer specified. Having the inputs and the assumptions, this problem can be formulated as a variant of the famous VRP with time windows. This part is not the focus of today's case. So we already formulated this problem for you, and you can find the formulation and all the description inside of the technician routing notebook that you can check it on your own to see how it's formulated. So if this was not the problem, then what are we trying to solve here? Well, let's find out. The technicians are not the only limited resources that we have. The service vans are often in shorter supply than the technicians. The current approach is to dispatch a technician with a van as soon as we know their schedule. When a technician returns to the center, then the van becomes available for others to use. The company noticed that the vans are not being utilized very well, and they believe they can do better. And that is the focus of our current case study. So let's first take a look at the output of the TRS model to see which customers are assigned to which technicians and in what order. We have two output tables. One is the orders, where it has information about each customer, whom they're assigned to, and then the earliest and latest windows where the technicians can visit them. So for example, if we look at here, we are seeing that customer 2 is assigned to Bob, right? And it has a window availability between 30 to 150, right? But we see that the earliest time that Bob can visit the customer is 50. That's the earliest that Bob arrives at the customer. It's 50 because it takes him just 50 minutes to get from the service center to the customer's location. If you go and check the locations table in the previous slide, you can confirm that for yourself. Now, considering how long the job itself takes, which we see here it's 30 in the processing time column, the earliest end time for Bob is 50 plus 30, which is 80. And we are seeing it here as well, right? Here. So similarly, and since the customer gave us a 120-minute window because it says I'm available between 30 to 150, right? So it's a total of 120 minutes time window. We see that the latest time that Bob can arrive at the customer is 150, right? So we see here that for each job, there is a bit of a wiggle room. In this case, Bob can go to the job anytime between 50 and 150, and that's totally fine. Now, let's focus on the second output, which is the routes. Since we talked about Bob, let's also take a look at route 2, which was the route that Bob is assigned to, right? And you will see here that it takes him overall 100 minutes just in travel. And that makes sense because it was Bob only does one job, right, as we see here. And it takes him 50 minutes to get to the customer and 50 minutes back. So it's obvious that it He takes 100 minutes just in travel. But it also takes him 30 minutes to finish the job. So if Bob starts at the earliest possible time, which is 0, and takes all of the traveling time and processing time, the earliest finish time for him is going to be 130. If you repeat this calculation for the latest, you will see that the latest time is going to be 230, right? I know it's a lot easier to visualize this rather than looking at a table, so let's do that. So what are we looking at here? For each route, there are 2 bars, right? Because each route has a start to end window. And depending on whether the technician leaves at its earliest time or at its latest time. The length of each bar shows us the duration of that route. So if I go with the second route, which was Bob, we are seeing that if Bob leaves at its earliest time, which was 0, and takes the 130, that's the latest, that's the earliest finish time. And similarly, if Bob leaves at the latest time, which was 100, and takes the 130, he finishes at 230, right? So this chart shows us how much wiggle room each route has. All of this white space here that you see, that's the wiggle room, because I can start here, or that's the earliest to start, and that's the latest to start. So all of that is the wiggle room. I can start anytime in between that, right? Now, hopefully looking at this chart, maybe it's now more clear what the problem of that telecom company was and why they were not happy with their current solution. We said that the current solution, each technician leaves the depot as soon as their schedule is available. And when someone returns, then the vans are up for grabs. So in this plot, we see that in this approach, we need 4 vans, right? Because you have one here, one here, one here. So 3 of these vans, because the routes start at the earliest that the routes are available at 0. So I need 3 vans here and then another van here. Why I said 4? Because by the time route 5 wants to start, route 2 or 4 already are finished. They are back. So we can use those vans for route 5. But the question is, can't we do better here? If you look a bit more closely, then maybe you can spot an opportunity to use the route's schedule flexibility and find a way to use 3 vans. And that's what we need to do using mathematical optimization. Sure, we are using a very small data set here, but these types of problems are everywhere. Imagine if you run the same thing every day with hundreds of operators and customers from different locations in the country. Or imagine if you are the Amazon or Walmart of the world and you ship goods for much longer distances that can span days. In that case, your planning horizon is not going to be a 10-hour day, but rather it's going to be weeks. But the problem is the same. In fact, the solution to this problem, carried out for several months, may even reveal something else to the company. And that's whether they need to buy more vans to ensure not to lose their customers, or actually they have too many of them that are sitting idly. Or maybe they can see that by having a bit of a penalty, maybe in terms of some discount to the customer if they arrive a bit late there, they can cover more customers with the same resources. Essentially, this type of analysis helps us ask and answer the right questions. Now, I have to admit to something, and that is I cheated here in this plot. And I completely ignored the fact that technicians are stationed at different centers and we don't go from one center to another. But regardless of this little deception of mine, for the sake of the exercise, I just hope the motivation and importance of this exercise is clear to you. And if you're too hung up in that little deception, the fix is super simple. You just need to iterate over each center separately and run the analysis separately. All right, now that we have seen all of this, let's formally state the problem that we want to solve. Based on the outputs of the technician routing notebook, which will serve as the inputs for us, and knowing which technicians serve which customers, assign the routes to the vans with 2 objectives in mind. 1, maximize customer coverage. which means we don't want to fail to serve any of the customers that we already routed. To understand why this is important, just think what happens if we only have 1 or 2 vans. Clearly, we cannot cover every route and by extension every customer. So if we have to make that difficult choice of not serving some customers, how can we make sure to maximize the customer coverage? And the second objective is to minimize the number of vans used. So if I have 5 vans and 5 routes, I still prefer to use fewer vans rather than assign 1 van to each route, which makes sense. All right, before we formulate this problem together, I want you to take some time and think about the model yourself. You know your objectives, but what are your constraints? What are your decision variables? All right, let me give you a few hints. You want to assign routes to vans. So that one should probably be a decision variable. But what else? Maybe you can take some clue from the objectives of the model. What can be the constraints here? You saw in the plot in the previous slide that we somehow want to take advantage of routes schedule flexibility, and if possible, have multiple routes be assigned to a single van. So it seems there also needs to be some relation between routes when they are assigned to a van, right? Also, we said taking advantage of the route's flexibility. But how do you define that flexibility? It's not that the route can start or end anytime at once, right? If you think about the answers to these questions, then hopefully you have a better sense of what variables and constraints we need for this problem. Good luck.